So, in this particular lecture we are going to look at the Falkner-Skan class of solutions. It is basically the Falkner-Skan transformation to develop self-similar solutions for wedge flows. Okay. So, the solutions can be of different types. Let me see. So, if you look at it here, for example, okay, so this is one type of a wedge. Go to the PPT view. Okay. So, this is one type of a wedge. Okay. So, the angle subtained is beta pi. Okay. This is one type. Okay. So, this is u infinity still t infinity. This is how the direction of x is actually measured. Okay. So, this is more like a convergent channel kind of a flow, whereas the other part that you see, this is also another wedge, okay, where the flow is a little bit diverging. This is minus beta pi. Okay. So, the flow, this is the direction of x, it is still u infinity t infinity, okay, and the angles, these angles can go, it can be anything that you want. Okay. So, when it becomes flat like this, it becomes a Hyman's flow. Okay. When the angle goes to 0, it becomes basically the flat plate boundary layer. Okay. So, in between, and when it goes to the other extreme, basically crosses the 90-degree mark, you get these kind of solutions. Okay. So, the Falkner-Skan class of solutions basically is applicable for any type of wedge where the incoming flow is always uniform in terms of velocity and temperature. Okay. So, based on this, let us go back. So, first and foremost, the first assumption assumption 1, u infinity is equal to C1 x to the power of m. Okay. Where does this come from? We promised that we will cover the origin of this. It basically comes from the potential flow theory. Right. Outside the boundary layer, okay, the potential flow theory dictates that C1 must be equal to u infinity should be equal to C1 x to the power of m. Similarly, T minus T naught minus T infinity, where T naught is the temperature of the wall, okay, is given by C2 x to the power of n. Okay. N and m are different as of now, remember that. Okay. Here we try to establish the relationship between the two. M is equal to beta by minus 2 by beta, 2 minus beta, where beta greater than 0 implies that the flow is accelerating. That means it is like a channel flow. Okay. Beta less than 0 implies the flow is decelerating. That means it is basically a diffuser kind of a flow or a divergent nozzle. Beta equal to 0 implies a flat plate. Beta equal to 1 implies a stagnation flow. So, you can see the corresponding m's you can find out from this particular thing. One thing you can notice is that when beta is equal to 0, m is also equal to 0. So, flat plate basically corresponds to m equal to 0. Does that obey with this? Because as you put m equal to 0 in this particular expression, your u infinity becomes a constant, which is the correct thing, right. For a flat plate with no inclination, your u infinity, that is your free stream velocity, is not a function of x, right. Okay. So, that is easily you can see that that is the condition over there. Okay. Similarly, m is also equal to 1 when beta is equal to 1. Okay. Got it? So, m equal to 1 because beta is equal to 1, that would mean that u infinity should be equal to C1 into x, right. So, that would mean this type of thing, if you recall your fluid dynamics or viscous fluid flow, this actually typically corresponds to a stagnation type of flow, right. So, this kind of agrees, whatever our strategy was, is kind of agrees with the view that we have linked it with beta, where beta is basically the wedge angle, right. Okay. Let us, based on this, let us try to see how we can actually best define the whole framework once again, the self similarity solution, because that is what we promised. Okay. So, neta is equal to y over delta to y u infinity by gamma x, u infinity is equal to C1 x to the power of m, neta is equal to y into C1 by gamma x m minus 1 by 2, right. Okay. Psi, which is basically the stream function, this we already defined in the general case of suction and blowing. Some parameter space like this, right. Now, let us do the transformations. D psi by dx is slightly different of how we progressed with the self similarity solution with a flat plate, but we could have done it also in this way. So, there are different routes, essentially the thing remains the same, you are free to use whichever one you are most comfortable with, by d neta by dx, d psi by dx. Okay. Now, neta is given as y C1 by gamma x m minus 1 by 2, right. Okay. This is also given. So, therefore, this leads to, these are all mathematical transformations. So, it just requires that you just work out the math, okay, in more details. Which gives you got it. So, d psi by d neta is equal to okay. Similarly, d psi by dx equal to okay. So, this is after this, okay, after this. So, these are the different types of transformations that we are actually doing over here, okay. So, similarly, d psi by dx. So, this is the stream function approach to the similarity solutions. The flat plate can also be done in a very similar way, but we chose to show two approaches in two problems so that you can adopt any one of them, okay. So, therefore, d psi by dy okay. So, now we already know this is your u. So, therefore, this will be okay, and u is basically equal to u infinity f prime neta. So, you can see that it kind of agrees. We started with this particular expression first, right, in our previous approach. You can see that these two things are basically equivalent to each other, right, except u infinity instead of a constant, now it is C1 x to the power of m now. Given by that, if I write the full expression, because there are a few steps which I am going to skip over here that you can work out. This is what we wrote in our general case of suction and blowing also. This comes basically like this. Okay. Now, if we can do a check, if m equal to 0, which is basically the flat plate boundary layer, your V becomes equal to u infinity into gamma by x into half minus neta df by d neta. So, this is correct, right, this is quite correct. Okay. Now, to go to the momentum equation, we need to find out terms like du dx plus du dy, d square u dy square, etc., etc., right. All those things needs to be found out. Okay. So, let us write du dx is going to be long because we are carrying a few terms with us now. Okay. F prime plus C1 equal to got it. Okay. So, that is du by dx. We are doing it term by term so that we can collect it at the end. Okay. Du dy will be equal to okay. So, that is the first derivative. Similarly, okay, that is the other term. Okay. Now, we feed all this information to the conservation of x momentum, which is basically u du dy plus v, sorry, okay. Here of course, your pressure term dp by dx is minus u infinity du infinity by dx, right. This comes from the Eulers. Right. Okay. So, now what we do is now you put all these values of u, v, du dx and all these values, and the final form of the equation therefore, now it is term by term substitution. that is the total expression that you got, okay, in this particular. Okay. So, as you can see, once again, if m is equal to 0, what will happen? Okay, this equation will become 2f triple prime plus f into f double prime. This entire term goes to 0. So, you will get a 0 over here. So, this will lead to f triple prime plus half f by f double prime is equal to 0, which is like the flat plate boundary layer equation. Okay. We once again get the same thing, the flat plate boundary layer. Okay. But this is the total expression when you actually have a wedge solution. Okay. So, this is a general class of solution, more generic than your Falkner, than your Blasius boundary layer. Okay. So, the boundary conditions will be, okay, u equal to 0 at y equal to 0, that leads to u equal to 0 at neta equal to 0, leading to f prime is equal to 0, v equal to 0 at y equal to 0, leads to v equal to 0 at neta equal to 0, leads to f equal to 0, right. U equal to infinity at y goes to infinity, leads to f prime as neta progresses to infinity is equal to 1. These are the sets of boundary conditions that you have. Okay. So, now, okay, as soon as these things are done, okay, so let us now look at, okay, what the boundary layer profiles are going to look like before we go to the energy equation and see what the energy equation should look like. Okay. So, let us look at this particular expression over here. Okay. So, these are for the different betas. This is basically nothing but the velocity profile u by u infinity, right. Okay. So, as you can see, beta equal to 0 once again is a flat plate boundary layer. Let us mark that line. So, this is basically your flat plate boundary layer, right, basically your flat plate boundary layer. In this particular direction, you can see that the boundary layer is basically sagging a little bit. Okay. That is where the point is that your beta starts to actually become negative. Okay. And in this particular direction, on the other side, the beta is actually increasing. Okay. So, this corresponds basically to a diffuser, that corresponds to a convergent nozzle, right. Okay. Now, as you can see from a diffuser, what happens, very standard things, as you have a diffuser, what happens is that the flow is basically facing what we call an adverse pressure gradient. As the pressure, as this diffuser angle becomes larger and larger, the flow will at some point of time starts to separate. Okay. And that separation happens at around beta equal to 0.198, okay, approximately close to minus 0.2. Okay. As you can see, the boundary layer profile is almost equal to 0, because the shear stress is nothing but the slope at this particular point, right. So, as you can see, the boundary layer is sagging, okay, and it is actually equal to 0 at the walls. That means the wall shear stress should be equal to 0 at this particular point, right. So, as you go on increasing the diffuser part, okay, chances of flow separation increases, and as the flow separation increases, you actually have separation of the shear layer. As you have separation of the shear layer, the flow basically therefore separates. On the other side, however, the boundary layer becomes sharper and sharper, as you can see, right. Okay, it becomes sharper and sharper. This is based on the similarity parameter, which is basically your neta. Okay, and therefore, the shear stress will also become higher and higher. Okay. So, we can write it here, when beta is equal to 0, boundary layer is thin. This is corresponds to the accelerating flow, which is basically the nozzle flow. Beta less than 0 means the boundary layer is thick. This is like a retarding flow, right. Okay. So, tau is basically given as du dy at y equal to 0, right, which translates to tau is equal to mu u infinity by x double prime is equal to 0. So, therefore, Cf, okay, should become 0 into Reynolds number to the power of minus half. This is a function of beta, which is quite obvious from this particular graph, that as you increase beta, okay, your u by u infinity profile changes. As a result of that, your f double prime equal to 0 profile also should change. Because of that, you are going to have this kind of thing. Okay. So, this is quite apparent in the next plot. If you look at this, okay, this is flow over a wedge. So, this part is once again the beta, the same thing. Okay. This is like, as I said, flow through a diverging channel, and this is the flow over a wedge, right. Okay. So, as you can see that this is basically nothing but your shear stress, the wall shear stress. This is your f double prime equal to 0. As we saw, Cf was proportional to this, correct. So, we can see in this particular case at 0, this is what is whatever the value that is you get from your self similarity solution. As you go to about point minus 0.2, okay, everything separates and you basically get 0 shear happening over there. Beyond this, there is separation. Here, of course, you can see that the shear stress will continuously increase. So, it is very much like their suction and blowing kind of a stuff, except that here the boundary layer thickness is varied just by changing the channel wedge, that whatever is a wedge angle, we are varying that and we are able to get this extraordinarily nice profiles coming out of this. Okay. So, based on this, okay, we can certainly say that Cf will be reduced, as beta is reduced, right, becomes Cf is equal to 0 at the point of separation, right. At the point of separation, Cf becomes equal to 0. So, from this particular profiles, that what we have done over here, we saw two important things is that when the flow is accelerating, the boundary layer is always thin. When the flow is decelerating, the boundary layer is always thick. Okay. So, that is proven through this analysis, and the shear stress, which is dependent on the profile, the boundary layer profile essentially, or basically the angle at the wall, that also changes, okay, with the wedge angle. Now, coming back to our journal. So, therefore, we can readily see the estimates that wedge flow is self similar, right, is self similar, okay, and Cf is actually given by f double prime 0, which is a function of beta that we saw. As beta goes up, or rather beta comes down, Cf also comes down, right. Cf is equal to 0 when beta is equal to minus 0.198, okay. Cf goes up when beta goes up, right. So, these particular things, and if you look at what we did, all these mathematical calculations, okay, yielded that this is the basic governing equation, right, which we basically solve in a very similar way that we did earlier. That means using the shooting scheme and things like that. But even without the shooting scheme and without all these things, the basic problem remains that the solution pattern remains the same, except that the boundary layer is accordingly modified depending on whatever is the value of this m going to be. That means whether it is, this m is nothing but your beta, remember m is your beta actually, okay, and the special forms can all be derived from this particular expression, right. So, we are left with, in the next class what we are going to do is that we are going to look at the energy equation now, okay, because the energy equation comes after this. Now, we have solved the momentum, we know how it looks like, we have explained what is the nature of this profile is going to look like, but we are going to see that through the energy equation what we can get, that whether the energy equation is any different or whether it predicts something very similar, that also we will see by looking at the results. Okay. So, in the next class we are going to go into the energy equation mode, but the wedge, now it is very clear that how we got those equations in suction and blowing. Okay. Suction and blowing physically kind of represents the same thing as your wedge solution. It is all about changing the boundary layer, thickness of the boundary layer. If the boundary layer profile changes, everything changes, right from your shear stress to your wall heat transfer coefficient. Thank you.